And I am here to present my work on the topic of evolutionary computing based neuro-computational model for microstrip patch antenna design configuration. Yes, sir. Here are the outlines of my work.
Miss Rohini, if you don't mind,
Yes, sir.
can you make the full screen view, please? So it will be easy for
Screen.
everyone to see.
Full screen.
In the right bottom.
Yes, sir. Yes, sir.
Yep. Can you see the 70% in the right bottom?
So just wait.
No, go down to the bottom, right side, right bottom. Yep. Thank you.
Here are the outlines of my work: introduction to microstrip patch antenna, analysis methods of microstrip patch antenna, design of microstrip antenna, design procedure of microstrip patch antenna using artificial neural network, design procedure for microstrip patch antenna using ANN, AGA algorithm. AGA stands for adaptive genetic algorithm, results and discussion, conclusion, and finally the references. Now come to the microstrip patch antenna. Microstrip patch antenna, in its simplest form, consisting of a radiating patch of one side of dielectric substrate, which has a ground plane on the other side. The patch conductor may be of copper and gold and can assume any shape. The advantages of microstrip patch antenna like lightweight, inexpensive and robust, easy to fabricate, easy to feed, easy to use in an array or incorporate with other microstrip circuit elements. Dual frequency antenna can be made easily. However, microstrip patch antenna suffers from some limitations also, like the narrow bandwidth, low efficiency, low gain, low power handling capacity, surface wave excitation. There are various methods to overcome these problems. Now come to the applications of the microstrip antenna. Patch antenna can be found in both planar as well as non-planar surface design that make it suitable for the application serving like satellite communication, remote sensing, defense communication, radio frequency identification purposes. Low cost and easy to fabricate make it suitable for numerous wireless transmission purposes. For microstrip patch antenna, the selection of optimal design parameters such as patch length, patch width, substrate thickness, dielectric constant, and suitable feeding method to operate over the targeted frequency and over extended bandwidth is a highly iterative task. With search motive, data-driven machine learning-based methods have been proposed to estimate suitable set of design parameters for microstrip patch antenna, especially to be used for ultra-wideband applications. Some of the key methods such as neuro-computing concepts perform design parameter estimation. Now come to the artificial neural network. An artificial neural network, usually called a neural network, is a computational model or a mathematical model that tries to simulate the structure of biological neural network. It consists of interconnected group of neurons which process information using connectionist approach to the computation. The mentioned figure best shows the analogy between a neuron and a node. First, in a neuron, the input like heat, pain, etc. are perceived by the data, processed by the cell body and sent to the brain via axon. So at a node function, it receives input, processes it, and gives output. Just like a brain, the data is transferred from the input to output to the best of its ability. Neural network depends upon the training data, which can help them to learn and to improve their accuracy over time. Once this neural network improve their accuracy, they are power tool in the computer science and artificial intelligence. Function like the image processing and the speech recognition can take minutes versus hours when compared to the manual identification by human experts. One of the common artificial neural network is the Google search algorithm. Now come to the design of the microstrip patch antenna. Before discussing the proposed model and its implementation, it is useful to understand the design consideration and the applied mathematical model. For this motive, the parametric definition of the rectangular microstrip patch antenna is given in the subsequent section. To obtain the final design solution, adaptive genetic algorithm ANN requires different training parameters with the resonant frequency in the ultra-wideband ranges. At first, the resonant frequency of 4.99 gigahertz is considered with the dielectric constant of 4.4, while the height of the dielectric substrate was maintained at 1.6 mm respectively. With these initial parameters, the length and the width of the patch is obtained using the mathematical equations given over here. Using the obtained length and width of the patch are 13.34 and 17.7 mm. By using equation number 7, we can find the width of the microstrip feed line, which is 2.94 mm. For ultra-wideband application, the lower cutoff frequency was maintained at 4.94 gigahertz, while the higher cutoff frequency was maintained at 5.95 gigahertz. By varying the dimensional parameter while retaining the other parameter constant, few samples are obtained, which is used for the microstrip patch antenna synthesis using artificial neural network and further enhanced AGA-ANN model. Now come to the microstrip patch antenna synthesis. Excuse me. Here, the different algorithms like GDNN, ANN, RBF, LMANN has been explored extensively due to the ability to process large set of input data in low computational time. For microstrip patch antenna synthesis, we applied different variants in additional to the proposed AGA-ANN model, where we feed different cutoff frequencies parameter, dielectric constant, and height of the dielectric constant as input to obtain the two optimal values of the patch length and patch width. As shown in figure 4, ANN model consists 3 layers: input layer, hidden layer, and the output layer. At the input layer, the 3 parameters, which are the height of the dielectric substrate, dielectric constant, and the resonant frequency, is fed as input. At this layer, linear activation function is applied, which enables the output of the input data is equal to the input of the input data. At the hidden layer, we applied sigmoidal activation function, and at the output layer, 2 neurons are active, which is the length of the patch and the width of the patch. To achieve the optimal values of the length and width, ANN requires to reduce error iteratively. For this, mean square error is considered as error function to obtain the optimal values. Here, the learning rate is 0.01, and while the stopping condition or the error is considered as 0.001, which means ANN keep on iterating till achieving an error of 0.001. Different ANN variants have different performance. Considering this fact, in this paper, we applied different ANN variants and their respective performance is examined. Now come to the GDANN, gradient descent artificial neural network. Gradient descent is an optimization algorithm which is commonly used to train machine learning models and neural networks. Training data helps this model to learn over time, which improves its accuracy with each iteration of parameter update. For gradient descent, to reach the local minimum, selection of appropriate learning rate is important, which is neither too low, neither too high. If it is too high, it may not reach the local minimum because it bounces back and forth between the converse function of gradient descent. If it is too low, it eventually reaches the local minimum, but it may take a while. In the given equation number 12, FWX is a non-linear in the weight vector W. Lambda is the regularization factor and R is the cost function. For equation 11, ANN-GD intends to find the local minimum using gradient descent algorithm. Using equation 13 and 14, gradient descent updates the weight iteratively by replacing W by WT plus 1. Here eta t is the learning rate, usually decreases with t. Delta L states the error. Now come to the RBF-ANN, radial basis function artificial neural network. Radial basis function neural network in its simplest form is a 3-layer feed-forward neural network. The first layer corresponds to the input layer of the network. The second layer is the hidden layer consisting of a number of radial basis function activation units, and the last layer corresponds to the output layer of the network. Activation function in radial basis function are normally implemented as Gaussian function. Now, the output of the jth activation function phi j in the hidden layer of the network can be calculated using equation number 15 based on the distance between the input parameter x and the center j. Here Cj and Oj, phi j, sorry, Cj and phi j are the width and the centers of the hidden neuron j. Now, during the training phase, radial basis function can be performed in 2 stages. In the first stage, center and widths are found using some unsupervised clustering algorithm. In the second stage, the connection weights between the hidden layer and the output layer are obtained in such a way that the error is minimized over all the data set. Now come to the Leavenworth-Marquardt algorithm. LM algorithm is used to solve non-linear least square problems. This curve fitting method is a combination of 2 other methods, the gradient descent and the Gauss-Newton. Both these methods are iterative algorithms, which means they use a series of calculations to find a solution. In equation number 16, Wj signifies the current weight, while Wj plus 1 states the updated weight. Here, I is the identity matrix, J is the Jacobian matrix, and mu represents the combination coefficient. Equation 17 presents the mathematical expression for the Jacobian matrix used, where N states the total weight, P presents the input pattern, and M presents the output pattern. As well as we already know that LM-NN algorithm is having the efficiency of both AGA-ANN as well as GD-ANN. While varying the value of mu, it can operate it as both GD-ANN as well as SG-ANN. As shown in figure 5, for each output pattern M, the proposed model estimates the error value EK. After then, which is processed for the Jacobian estimation as given in equation number 17. After then, we apply equation 16 to find the weight value to reduce the error EK plus 1. Assigning the higher value of mu enables it to function as SDANN, while lower the value of mu enables to behave as a GDANN. Once finding the estimated error EK plus 1 is less than EK, the proposed model updates the learning coefficient mu, which is used as a feedback to update the weight value. This process continues till the error EK plus 1 is less than Emax. This stage signifies the convergence stage, where it predicts the targeted class. In the above process, we find that the estimation of the weight parameter is a highly iterative task, and it forces the algorithm to undergo local minima and convergence, which can impact its accuracy and reliability of the design parameter estimation. This problem becomes more severe when a number of weight parameters to be estimated. Considering this fact, in this paper, we proposed evolutionary computing based artificial neural network learning model. The adaptive genetic algorithm is a method for solving both constrained and unconstrained optimization problem that is based on the natural selection, the process that derives biological evolution. The genetic algorithm repeatedly modifies a population of individual solutions. A detailed discussion of adaptive genetic model is given as follows in figure 7. Initially, Basically, in the first step, we need to select the population. We need to initialize the population. A population means whatever the input we are giving. Basically, we are not giving a single data. It may be 2 or 3 or 4. And all inputs are combinedly called the population here. Once the population has been selected, we go for the convergence. Convergence means we reach the requirement, or can say we reach the threshold percentage. That is some check condition here. Did we reach the required solution or not? If yes, then stop. Else, repeat the process. Repetition is nothing, but the first step is the selection, and the second step is the reproduction. In the selection, we calculate the fitness value. Fitness value. So what is fitness? Basically, we are taking example. Basically, if a person is going to a gym, we are saying it is a fit person. If it is not going gym, it is not a fit. In that way, we can select the fitness value. And after then, we perform weighting. In the fitness process, we can select the two best solution, and after perform the meeting. Before this selection process, we have to do some operations. That is the crossover and the mutation. At the end, we get a result, which is again add to our population. If our previous population size is 10, and we having ninth one is the worst, means it is not satisfying any requirement, then that ninth one is replaced by our new one. And then we again check the convergence. This process continues till we get the best one. So that is the logic here. Microstrip patch antenna design verification. In this work, our aim is to identify the optimal dimensional parameter of the rectangular microstrip patch antenna for ultra wideband application. For this, our antenna was designed with the parameters: height of the substrate, dielectric constant, the patch width, and the patch length. At first, the training parameters were obtained by varying dimensional parameter while maintaining the dielectric constant and height of the dielectric constant. Frequency values were obtained. The obtained results are given in table number 1. Table 2, 3, and 4 shows the dimensional parameter obtained by using different ANN variants such as ANN-GD, ANN-LM, and ANN-RBF. By observing the result, it is found that a patch antenna with 0.3175 centimeter height, 1.40 centimeter width, and 0.701 centimeter length with 2.330 dielectric constant can achieve the highest cutoff frequency, that is 8.926 gigahertz. So considering the key features of ANN-based method like local minima, and convergence, in this paper we applied a adaptive genetic algorithm ANN for learning enhancement and dynamic weight estimation. For microstrip patch antenna synthesis, we maintained 3 input neurons, 6 hidden neurons, while 2 neurons were defined as output to obtain 2 patch dimensional parameter width and length. The simulated result obtained by AGA-ANN model is given in table 5. Results obtained in table 5 clearly show that among the different possible design configuration, microstrip patch antenna with 0.3175 centimeter height, a dielectric constant of 2.330, and dimensional characteristic length 4.845 centimeter and width of 6.922 centimeter achieves the highest cutoff frequency of 9.140 gigahertz. By observing table 4 and 5, we see the highest cutoff frequency obtained by ANN-RBF is relatively small and hence low cost than the best performance delivered by the AGA-ANN. As our proposed work does not perform the physical verification like the radiation pattern and VSWR, it must be assessed whether the performance delivered by the two is accurate, and which should be generalized as the best solution consideration. So considering this fact, we compute the error for each neuro model. by using these equations. Now, as shown in table 6, in comparison to the other computing models, AGA-ANN exhibits minimum average error of 0.0014. Mean magnitude of relative error is 0.0045 and standard error of mean is 0.424, which indicates that the AGA-ANN provides more accurate prediction than the other neurocomputing models. Thus, we can say that AGA-ANN model are superior even though it shows higher dimension than the ANN-RBF model. As we see in table 6, ANN-RBF shows higher error than the proposed AGA-ANN model. Considering this fact, its resulting output, the length and width have further been applied for the microstrip patch antenna design verification. For that, ANN was modeled as we see here, this is our final diagram. The ANN was modeled as with 4 input neurons, 6 hidden neurons, and a single output neuron, that is the cutoff frequency. Observing the over result as shown in table 7, it is found that a rectangular microstrip patch antenna, see table number 7. Yes. See in table number 7, it is found that rectangular microstrip patch antenna with 3.17 millimeter of dielectric substrate height and dielectric constant of 2.33 with patch width of 14.78 millimeter and length of 11.08 millimeter can achieve the maximum resonant frequency of 8.23 gigahertz. By observing the overall result, it is clear that the dimensional parameter of microstrip patch antenna are small enough to fulfill the miniaturization aspects while delivering the high resonant frequency of 8.273 gigahertz, which is suitable for numerous ultra-wideband application. Finally, come to the conclusion. In this paper, our objective was to train the artificial neural network model to obtain an optimal set of microstrip patch antenna design parameters for ultra-wideband application. The proposed AGA-ANN based neurocomputational model shows that a rectangular microstrip patch antenna with 3.17 millimeter height, 2.33 dielectric constant and 14.78 millimeter width and 11.08 millimeter length respectively can achieve the maximum resonant frequency of 8.23 gigahertz, which is sufficient for low size compact microstrip patch antenna for ultra wideband application. Here are the references. Thank you.